Um, the next speaker for this morning for me, although it's the evening over there, is Jack Laiho from Syracuse University, and he'll tell us about lattice quantum gravity and asymptotic safety. Go ahead, Jack.
All right, thank you. Okay, so I'm going to talk about asymptotic safety and how maybe we could study this, in particular for the scenario for gravity, and how we could study this on the lattice. So just a little background before launching into results and formulation. So Weinberg proposed the idea that gravity might be asymptotically safe in 1976 in a set of Eriche lectures. This scenario would entail that gravity would be effectively renormalizable when formulated non-perturbatively, and that the problem lies with perturbation theory, since we know gravity is non-renormalizable perturbatively. But maybe the problem was perturbation theory, not general relativity. But this was a long time ago, and this just highlights how difficult it is to address this when you have to use non-perturbative methods. So the lattice is one such non-perturbative method. It's sort of a very powerful method. And so in a Euclidean lattice formulation, the fixed point would show up as a continuous phase transition point, the approach to which would define a continuum limit. And so this sort of idea is to try and formulate the thing on the lattice and study the phase diagram and see if you can find something that sort of looks like Euclidean quantum gravity. Okay. So lattice gravity has a sort of longish history at this point. People first came up with this idea called Euclidean dynamical triangulations, which is kind of a mouthful, so EDT for short. And this was a lattice formulation introduced in the 90s. It turns out it works perfectly in 2 dimensions. It agrees very nicely with matrix models and non-critical string theory. But as soon as you go to 4 dimensions, you get these unphysical phases and things kind of don't look as good. So the idea is that the lattice geometries are approximated by triangles with fixed edge lengths, and the dynamics is contained in the connectivity of the triangles, which can be added or deleted. Added or deleted in Monte Carlo time. I mean, basically, you're sampling the path integral using numerical Monte Carlo methods. So I've been working on this for a while, and things actually started looking kind of interesting, or maybe good in a few years ago. And the idea is that maybe we need to fine-tune some of the Baire parameters in EDT in order to recover the correct continuum limit. I mean, one fine-tuning was it was already known that you need to adjust the Baire cosmological constant to take an infinite volume limit. But that infinite volume, that's an infinite lattice volume. You could still end up in a phase that's sort of pathological that has no spatial extent, so that effectively the renormalized cosmological constant is sort of order the cutoff scale. So very large, with these universes of basically 1 or 2 lattice hops of spatial extent. I'm talking about a different fine tuning, in this case of an ultralocal measure term, which I'll come to. And this tuning is sort of in analogy to using Wilson fermions in lattice gauge theory to study quantum chromodynamics with lighter massless quarks. And you see there strong similarities are seen. So just to write down, I mean, this is just sort of schematic. This is the continuum partition function of Euclidean gravity along with the Einstein-Hilbert action. And we discretize this, so we use the Euclidean Reggie action. And so this first term is the Einstein-Hilbert term. You can see that this involves a deficit angle around a triangular face. And then the second term is the cosmological constant term, which just involves a sum over 4 simplices. So this is just a volume term. And so the idea is to put this action into the path integral and do the importance sampling. But people tried this in the 90s and got these unphysical looking phases. So you can't just do that. But one of the things that also was introduced in the 90s was this sort of ultra-local measure term here. So this is sort of inspired by continuum arguments that think that maybe the partition function should look like equation 4 with some non-uniform weighting of this measure term. And this is kind of motivated by this Fujikawa measure term. Fujikawa suggested a while ago that if your regulator breaks scale invariance, so almost everything besides dim reg, then you have to worry about your local measure terms in order to ensure that there are no gauge anomalies, or in gravity, there are no diffeomorphism anomalies. And so in a sort of hand-waving way, or we could use the word ansatz, we can assume, or we can try and put something like this by hand into our calculations. Now in Fujikawa's calculation, he can show that diffeomorphism invariance, basically the absence of anomalies, ensures that gives beta some fixed value. But I'm arguing that this fine-tuning that we have to do is a sign that the lattice is actually breaking continuum diffeomorphism invariance, which doesn't sound crazy given that it's a lattice. And so you may not, you certainly don't have continuum diffeomorphism invariance. And the lattice analog of diffeomorphism invariance, which is sort of this rewriting of the vertices, invariance under sort of relabelings of the vertices, is a discrete symmetry at best. And so maybe a term of this kind where beta is allowed to float, or it becomes an adjustable parameter and has to be fine-tuned, could be the thing that we need to restore diffeomorphism invariance at finite lattice spacing, at least to some extent, kind of like chiral symmetry is restored approximately at finite lattice spacing with Wilson fermions due to a fine-tuning, and then fully, the chiral symmetry is fully restored only in the continuum limit. And so I'm taking this as sort of my analog picture for gravity, and then we'll see how it works. So this measure term here, this product over local volumes, can be written as the product over the orders of triangles, i.e. the number of four simplices to which a triangle belongs. And so if you put that measure in for this and the Reggie action in here, and you glue together a bunch of four simplices and do sort of Monte Carlo, then that's my program, and that's kind of what we want to investigate. So, right. So so let's try and do that fine tuning and see if it helps. So how do we define success? So we need to show the recovery of semi-classical physics in 4 dimensions. And we need to reproduce general relativity in the appropriate limit, because general relativity is a very successful theory of our actual universe describing our world. Basically, to show renormalizability, there has to exist a continuum limit at a continuous phase transition, right? That's what's required for the theory to be UV complete. Okay, so how are the simulations done? So the methods, sort of a set of local update moves that are ergodic, were introduced in the 90s. I wrote new code from scratch and introduced with a former postdoc, Daping Du, a new algorithm for parallelizing the code, which actually exploits the fact that there's low acceptance in this model using this set of local moves, and it partially compensates for it. It was checked that it reproduces just the scalar code configuration by configuration, and depending on the machine, so this works with OpenMP, so this is for a shared memory parallelization, and depending on how many cores you have, typically what we have access to, it buys us about a factor of 10, which is good. I mean, for these sorts of things. Okay, so now I'm going to talk about the results. All right, so this right here is the 3-volume distribution. So this is basically arises from a shelling of the lattices. Remember, there are sort of you're just gluing together a bunch of simplices, so you just have their neighbor information. So there's no sort of coordinate system other than what you kind of have to build by hand. And so you can shell these geometries and look at them, look at shells 1 geodesic hop away. So basically look at the nearest neighbors of an origin 4 simplex, and then look at all of their nearest neighbors and all of their nearest neighbors until you've sort of traveled out through the whole lattice and counted them all. And then you take an ensemble average of that, and you plot it as a function of the geodesic distance, and you basically get this shape. Now, you can rescale this shape. Basically, you know what the 4 volume is, so you can take the 4th root of that and rescale the linear, what we think is this linear distance, by the 4th root of the 4 volume. And then this thing we're counting is, you're basically counting 3 volume shells, or what you would like to see as 3 volume shells. And so you can scale this by n4, the number of 4 simplices to the 3/4. And if that scaling, if the thing really is 4-dimensional, then then increasing the volume. So this is 4K, so that's a 4,000 4 simplex lattice, 8,000, etc. And so if this thing really is scaling, then these curves should, 4-dimensionally, then these curves should lie on top of each other. And so the fact that they do gives us some hope that we actually do have 4-dimensional geometries when we fine tune to this particular point in the phase diagram. So basically there's a first order line, and we want to sit as close to that first order line as possible, and follow that line out to to its continuous endpoint, which may or may not be, which may actually be at infinity in the set of bare parameters that we're using. So it's very analogous to Wilson fermions, where in the case of Wilson fermions, the Wilson action explicitly breaks chiral symmetry. And so you want to fine tune the bare mass to what turns out to be a first order phase transition, at least with most of the discretization, for the gauge action that are sort of popular today. And so you fine tune to close to this first order phase transition and follow that line to its continuous endpoint, which lives at...
Jack Simon has a question.
Oh, yes.
Oh, I was asking, I think you really answered my question, Jack, but I just wanted to ask you what values of the parameters where you were taking this distribution. So you already said it since I posted my question. So
right.
This is critical line.
Yes, this is very close to the critical line. And this is the only place. So if you don't do this very close to the critical line, then you try and do this finite volume scaling, then you get a value which is either very large. So this is the Hausdorff dimension, or the large long distance Hausdorff dimension, that ends up being sort of large, possibly infinite, in what's called the collapsed phase, and it ends up being 2 in the branched polymer phase. So neither of those look very good, but close to the phase transition, this thing ends up being 4. And that also turns out to be true kind of along the phase transition. So this is at one particular point. This is at beta equal. This is when you basically set that exponent in the measure term to 0. So you're not doing anything special with that local measure term. And so, in fact, some results were kind of seen that looked sort of like this even back in the 90s. For 2 lattice, maybe 2 volumes, people kind of observed that it might be close, the Hausdorff dimension might be close to 4. We actually have an additional volume at 32K, which I haven't plotted, which also lies on this curve. So that's kind of nice. So this curve is basically the shape of the lattice. And you can compare what this should be for Euclidean de Sitter space. So for Euclidean de Sitter space, so de Sitter space is basically an exponential expansion. So that's a cosh. And then when you analytically continue that, you end up with a cosine, and that's for the scale factor, right? And so this is the 3 volume, and so it should be cosine cubed, right? With the origin chosen to line up such that the peak is where it is. And so I can plot that, which is this black line here. And the points that you saw, one of the lattices that you saw on the previous slide is this sort of orange set of data points. But we can now adjust the bare parameters to go to different lattice spacing. So rather than sitting at sort of the same point, but for larger volumes, we can now move to different lattice spacings, moving along this transition line, the phase transition line. And so what we see, so I've color coded these things. These are in rainbow colored order. So from infrared to UV for the scale of the cutoff. And so what you're seeing is that if you go to coarser coupling than the one I just showed, that this sort of asymmetric tail actually gets bigger, and it's in worse agreement with what sort of the classical expectation for what this lattice should look like. But as you take what we think are finer lattices, and I'll tell you how I think they're finer lattices in a minute, then it actually gets closer to this curve. And so it looks like, you're taking a continuum limit, it looks like you're approaching the black curve. At least it doesn't look insane to think that you're approaching that black curve. Right, okay. And so this suggests that you actually are getting Euclidean de Sitter space out of the simulations in the continuum limit. Okay, so this is one measure of success, right? And this is Euclidean de Sitter space in 4 dimensions. But then we want to look at other things. So we could also look at the spectral dimension, which is the dimension of space-time defined by a diffusion process. So sigma is the diffusion time step on the lattice. So that's basically one hop from a 4 simplex to chosen at random to one of its nearest neighbors. And then you just repeat that step and you just hop about the lattice. So you're just kind of doing a random walk around the lattice. So P of sigma is the return probability. So the probability of being back where you started in a random walk after sigma steps. And there's a fractal dimension called the spectral dimension, which is related to this return probability by this logarithmic derivative. And so you can get the spectral dimension from this. This is, so in general, if you have a fractal, the spectral dimension won't necessarily agree with the Hausdorff dimension, which is a fractal dimension, which is defined via a more geometric thing, via like the Schelling process that I described. So sort of comparing the radius of a sphere to its surface area. So we can look at this. And we expect, again, that all these fractal dimensions should approach 4 at long distances because they have to reproduce the world which we live in, which is a smooth sort of continuous geometry. Although it may be highly fractal at very small scales, those aren't the scales we probe in our measurements. So to get the world right, to reproduce our world, this has to be 4. So, whoops. And so if you look at the spectral dimension just on one particular ensemble at some volume, I think it's 8,000 simplices at beta equals 0, and you calculate this logarithmic derivative and multiply by -2, you get these black data points, which are actually very close together with some errors. And you can fit that to some ansatz. So there are other people who have sort of formulated lattice gravity and sort of looked at this type of thing and this sort of running of this spectral dimension with scale. So I'm using the same fit ansatz as Jan Ambjorn and collaborators. And it does a good job of fitting the data. And this is a sort of a way of estimating what this thing is at infinite time step. So basically in the large distance limit, what is this spectral dimension? And so characteristic of other approaches to quantum gravity, so the renormalization group, and also this thing called causal dynamical triangulations, which is kind of like our approach, except introducing a foliation explicitly. They also get, this is Ambjorn and company, they get these results that look nice and 4-dimensional and de Sitter-like with a running spectral dimension. So I kind of went back to the original dynamical triangulations, the Euclidean version, without putting in any foliation, because I figured, well, if they can get it, you probably don't need to do the foliation, or at least it would be kind of disturbing if you did. And there might be some way around that by, sort of, there might be something one can do with the Euclidean case. So anyway, so we get kind of similar results to this causal, this foliated version of dynamical triangulations. But what you can see from this curve, from this extrapolation, that it turns out this number, if you go even all the way out to infinity, this number is sort of closer to 3 than it is to 4. And if you get the wrong number of dimensions of space-time, then you have the wrong theory. So so what happens? So that point, that ensemble, is this little green point right here in the middle. So this is plotted. This is actually taking those sort of infinite distance extrapolated values and plotting them as a function of 1 over v. And so you can see, so they're color coded again by lattice spacing. And so you can see that for 3 different volumes, that the trend is actually up as a function of volume. And that lattice spacing, again, these are color coded according to, sort of rainbow order from IR to UV, although we don't have the UV on here. You can see that we're going to, again, the extrapolation is sort of trending up. And so some fit ansatz, which is 1 over v in volume and a squared in lattice spacing, gives this extrapolation, which does take us to 4. And we actually have a bunch more points, which I didn't bother to make the plot, but we've been adding ensembles to this, and again, things are consistent with 4. I mean, it's still compatible. So this is kind of reassuring that we could maybe reproduce the correct physics. So I told you that I would tell you how we know whether we're going to finer lattices or not. And so this is the return probability that's used to calculate the spectral dimension, but before you take the logarithmic derivative. So just the return probability. And so this is at different lattice spacings. And so if we assume that this is some kind of universal curve, and we can rescale the diffusion time step, which is a dimensionful quantity, to get a universal curve, then that rescaling factor would tell us the relative lattice spacing. So these guys, again, rainbow ordered, and you can in fact collapse them onto more or less a universal curve. And that tells you the relative lattice spacings. And that would tell you that the ones—
Jack, Toby has a question.
Oh, yes, go ahead.
Yeah, maybe I missed it, but your original action didn't build in a particular number of dimensions, did it?
Well, it did, because I'm gluing together 4 simplices.
Oh, I see. I'm sorry. I see.
Yeah. But the thing is, you can glue together 4 simplices, and you can get these pathological phases that have long distance dimension 2. For example, the branch polymer has Hausdorff dimension 2 and spectral dimension 4/3. And we actually ran in the branch polymer phase quite a bit and sort of verified those numbers quite precisely, sort of to test everything.
I see. But for example, if you've taken 5 simplices, you would expect to get a spectral dimension of 5 potentially.
Well, we don't know, actually. If you take 5-dimensional simplices and ran in the branch polymer phase, you actually see the same branch polymer phase with the same Hausdorff dimension of 2 and spectral dimension 4/3. So, and in fact, you also get the same thing with gluing together 3-dimensional simplices. So it's not clear. So in some sense, the dimensionality is put in, but in some sense, but just because you put in the right dimensionality doesn't mean you're going to get it out. So getting out the right dimensionality is highly non-trivial. Now, I don't know if you'd get out the right dimensionality if you put in the wrong dimensionality, sort of by hand. That would actually be very interesting because nobody's really looked at this tuning procedure that carefully in sort of, modern times, by which I mean sort of, not the 90s. So it would be interesting to see what happens if you change the dimension of your building blocks very close to the transition. Yeah. So we can look at this return probability, and so we see, so they're rainbow ordered, and so the UV again is this blue, and so you can see that discretization effects are getting smaller as you take the continuum limit. And also, what's kind of interesting is that this long distance, this in some sense, because of the shelling, the way the shelling is done, these points out here are at long distances. And so usually discretization effects mess up your short distance, which is why I would sort of posit that this isn't agreeing perfectly with the curve, and that's okay. You probably have to go to finer, bigger lattices, such that these points move way closer together, and you push the discretization effects sort of further to the origin. But you're also messing up, the long distance, which isn't typically what happens. Typically, you put on your blurry glasses. It doesn't matter whether your Statue of Liberty is made out of sort of atoms or Lego blocks, right? If you blur your vision, you zoom out far enough, you don't see that, that detail. But if your regulator breaks a symmetry of the theory that's important at long distances, then you will mess up your long distance physics. Again, like chiral symmetry breaking in Wilson fermions messes up the pion sector, even though the pion is the lightest particle in the spectrum and thus the sort of the longest distance probe. So you can mess up long distance physics, and the sign that you're messing it up and that it's getting restored in the continuum limit is a sign that your regulator is breaking some symmetry, which is also compatible with the fact that we had to fine tune this measure term, whose sort of purpose in the continuum is to restore gauge invariance, or diffeomorphism invariance in case of gravity. So this is, so things are kind of, the picture is kind of holding together. So now we know, so this is how we know our relative lattice spacing. So now let's look at other things. So this is new work with my former grad student, Scott Basler. He sort of started this off, and then a new grad student who I kind of borrowed from the University of Heidelberg, who visited me for a semester in the spring, and last spring. And so the idea is, okay, so we have something that kind of looks like the Sitter space, but we would actually like to know, so first of all, we'd like to know what our lattice spacing is, what is G Newton? And second of all, can you kind of reproduce semi-classical fluctuations about de Sitter? So it isn't just, maybe you can, it's not so easy to get a 4 sphere out of these simulations. It took, 20 years, but it would be nice to know if it isn't just the 4 sphere, but if you're actually if you actually have gravity. So G Newton does not appear in the classical de Sitter solution, so you can't extract a G Newton from that. But it does appear when you consider the semi-classical expansion about of the partition function about the Sitter space. So I've written that down here in terms of lattice parameters. So this kappa 4 is basically the bare cosmological constant, up to some factors. And this kappa 4 crit is sort of the critical one, such that if you tune the bare cosmological constant, then you'll approach infinite volume lattices. And so this is in the effective action, this is the cosmological constant term. And this term here, the second term, would be the Einstein-Hilbert term, which dimensionally, just in terms of the 4 volume, we expect to scale as the square root of N4. And so this K right here should be proportional to A squared, the lattice spacing squared, divided by G Newton. And so if we, yes.
What does the sum over N4 mean here? When you have N4 in the various places.
Let's see. Okay, yeah. So this is actually the path integral. So this is sort of a reduced. This is really just a sum over all possible N4s. So this is the analog of this is just the discretized version of the path integral. So here, let me continue just to make this a little bit clearer. So for example, we can look at the expectation value of N4. And so this would be a sum over all possible N4 values weighted by N4. And so this would give us this expectation value of N4. So this is assuming a sort of saddle point expansion about de Sitter. So basically it's assuming that the only degree of freedom is the 4 volume. So if you do the saddle point expansion, basically minimizing the action, then you get this quantity, or you get this combination of the parameters, the bare cosmological constant at fixed volume and in the infinite volume limit, and this K, which is related to G Newton. So it's proportional to 1 over G Newton.
And to answer David's question, I think it's just a question of, in the previous expression for the partition function, Jack had summed out all the triangulations of a fixed N4. And so all he has to do at that point is sum over N4. And you're assuming though this, that entropy of configurations at fixed N4 goes exponentially in N4. Right, Jack, roughly speaking.
That's correct. That's correct. Yeah, and in fact, there's a lot of evidence that it does go exponentially as N4. And then the question is, which shows that the partition function is exponentially bounded for the right, for kappa 4 less than kappa 4 crit. And then the statement that the Newton term scales like root N4 is just a question on the subleading corrections to the partition function once you've summed out everything other than the overall 4 volume factor. And so that's a question for the simulations to answer, because we can actually plot. So K, if I solve, so N4 is actually fixed in the simulation. So this expectation value is really just a constant.
Yeah, that's what was confusing me.
Yes. But the point, yes. So in the simulations, this thing is just some constant. But it's a constant we can vary. It's something we have the freedom to vary. And so if you plot kappa 4 as a function of 1 over root N4, then you can kind of convince yourself that slope will give you this little k over 2. So the slope of kappa 4 plotted as a function of 1 over root N4. And the point is that if this relationship is true, then this thing should be a straight line plotted when you plot kappa 4 over as a function of 1 over root N4. And so we can do that at our tuned values close to the phase transition, sort of all those points that gave you, these curves where we've done our measurements. And we actually have to go, so even though we ran at multiple volumes, the phase transition actually shifts a bit as a function of volume. And so this equation here, this business of sort of figuring out what the difference between the actual kappa 4 and the tuned kappa and the critical kappa 4, that has to be done for fixed values of the other bare parameters. And so we have to simulate at multiple volumes, even for each of our nominal volumes, and then multiple volumes also at each lattice spacing. So there's quite a bit of running that's needed. And you have to go to larger volumes because you want to be in the same phase. You don't want to go to smaller volumes and end up in the branch polymer phase as that phase transition shifts. And so it ends up being fairly time consuming. So we ran for about a year and we got a ton of ensembles at multiple volumes in order to test this equation 10, whether this thing really behaves the way we'd like it to if you actually have this sort of instanton approximation. And this is just one of our set of runs. So each of these points is a different ensemble. And so this is an uncorrelated fit to a straight line, which actually gives a pretty decent fit, as you can kind of see even chi by eye. And so we can extract the slope from this thing. And so this slope, just by taking its inverse and multiplying by some overall numerical factor, which is calculable, you can get G Newton.
Simon has a question.
Yes.
Just a quick question, Jack. This is at beta of minus 0.6. How does it look at beta of 0?
Yeah, so at beta of 0, it also looks nicely linear.
So it still goes like 1 over root N4.
Everything, even at beta of positive 1.5, it also looks very linear. Huh. So every one of these, in fact, you can move quite far from the transition and actually get something that looks kind of linear.
I thought in the 90s, people had looked at beta of 0 at something like this.
combinatorial triangulations, it ends up, you have to go to quite large volumes to see the sort of asymptotic scaling. Whereas with degenerate, you can see it even at very small volumes.
Yeah.
So in some sense, So in some sense, this is
like 0.3 or something like that.
Yeah, it was more. Yeah, it was more. Yeah, it was more like 0.3. And if you sort of dropped the smallest volumes, maybe you could convince yourself it was 0.5, but it wasn't, very conclusive. Whereas with the degenerate, it kind of comes out very cleanly. So it's kind of like having this is a different class of, I'm using a different class of triangulations, which is a sort of, which relaxes the combinatorial manifold constraints, sort of for the experts. And so this is, it turns out to have significantly smaller finite size effects when it comes to resolving phase transitions. And this is another thing that happens to have, the asymptotic scaling seems to set in at much smaller volumes. So it's cleaner to use this in this class of degenerate triangulations. So all of our points have these nice slopes. And so you can get a very clean determination of G Newton at finite lattice spacing and finite volume. And then you'd want to extrapolate that to the continuum infinite volume limit. So this partition function, this approximation of the partition function, this is, we validated in some sense numerically that things are behaving in this way. And if we assume that it's actually the de Sitter instanton, then you have this continuum calculation. This is actually the Hawking-Moss instanton, or partition function evaluated to get this Hawking-Moss instanton transition factor. And so that tells you sort of what the partition function looks like. And if you just make this identification between the lattice parameters and the continuum, and this sort of also identifying this cosmological constant term with the continuum cosmological constant, you can solve for all of this, eliminate lambda, and then just get G Newton in terms of K and some overall geometric factors, which are known from, it's just the volume factors of, of a four simplex, an equilateral four simplex. So you can work it all out. You can get K in terms of G, and you can turn all those slopes into a G Newton. But we're not quite there because our relative lattice spacing came from the return probability using dual lattice hops. So we're basically measuring distance using the dual lattice to get our relative lattice spacing. And in fact, we have a whole other determination of G Newton, or one can in principle get G Newton by looking at particle binding. And so it's natural to use simplex units also in that case. And so we are measuring our G Newton in link units because that's what appears in the action. So we need to convert that into simplex units. And so we can do that just by doing something similar to what we did to get the relative lattice spacing, which is to look at the return probability on the direct lattice rather than the dual lattice. So in the direct lattice, you're measuring hops. You actually are measuring link, the hops are in link distances. And so those are in units of A, whereas on the dual lattice, it's in units of simplex distances. And you can see that the curves, if you rescale them, I've rescaled the direct lattice ones. You can see that the curves overlap pretty nicely, and you can get a pretty good determination of the relative scale or the relative distance. This is really just like converting, inches into meters or whatever. You just need to know what the conversion factor is. And so this gives us a pretty good measurement of that conversion factor. So now, doing this at, so you can do this at a bunch of different volumes at fixed lattice spacing, and I extrapolate that to the infinite volume limit. And so now I know how to infinitely correct for that conversion factor for infinite volume, and I know how to do it at multiple lattice spacings. So we can turn our G Newtons from that slope that I showed you into a G Newton measured in simplex units. And so that's what this is. So each one of these points, so we have multiple volumes here. That's these orange curves, or these orange points. And then we also have multiple lattice spacings. And so this L relative is the relative lattice spacing in simplex units squared. And so we're doing basically we're doing a 1 over V A squared extrapolation. And you can see this thing is curved in a squared. So we have an a squared and a to the fourth. It's also, there's some curvature in 1 over v. So we're doing an extrapolation, which is, kind of in the same spirit as what we used for the extrapolation to the spectral dimension, to sort of its infinite volume continuum limit. And so we can use that to get a value of G Newton, which then tells us what the Planck scale is, right? We can just take the square root of this and get the Planck length. And we have pretty good precision on this. We kind of know the Planck length, which means, we know the lattice spacing to sort of 7%-ish, if we trust these errors. And so that tells us that our coarse lattice spacing is around a fourth the Planck length, and our finest lattice spacing is around a sixth the Planck length. And so we're starting to push into, our lattice spacings are starting to, see some, hierarchy of scales between the Planck length and the lattice spacing, which is, getting ever smaller. So there doesn't seem to be a limit to how small we can push the lattice spacing, which is just another way of saying we can probably take the continuum limit, and that we're seeing scaling of the type that is sort of, you might expect, and out of this thing, which is this, and we can make contact with semi-classical physics and, and extract a G Newton, which appears sort of sensible and compatible with sort of our, our assumptions. Okay, so now I just want to tell you a bit quickly about adding matter to all of this. So we've looked at adding both scalar and fermion matter fields. So people added scalars and U1 gauge fields dynamically, unquenched, already over 20 years ago, or at least they sort of wrote down the model and implemented it numerically, without this sort of picture of the fine tuning and figuring out what you have to do to recover, semi-classical physics, continuum physics, that maybe, that needs to be revisited. And so for the moment, we're revisiting some things in the quenched approximation. So we're just assuming that matter loops are we're just neglecting them. Since this allows us to reuse existing lattice ensembles, and it's a long and venerable tradition to look at the quenched theory before doing the dynamics, just because it's easier. And so, so we looked at a scalar field. I'm not going to have time, I don't think, to tell you about fermions, but I will tell you about the scalars. Actually, the fermion stuff was work in collaboration with Simon and our postdoc, now at Fermilab, Judah Omotiaki. So this scalar work is done, again, in collaboration with Judah, also with Mark and a new student, Mingwei. And so a lattice discretization of this, so I've just written down the minimally coupled scalar field, or action of the scalar field, minimally coupled to gravity. And so you can write down this action. You can look at scalar propagators on our quenched configurations and do the usual things that you do in lattice QCD with those scalar propagators. For example, you put in some bare mass into this action, and you can see what the renormalized mass looks like coming out by looking at some Euclidean correlation function. And again, the covariant Laplacian is well defined on the dual lattice, just by taking finite differences of these simplex neighbors. And so, yeah, so we can get the propagator just by inverting this Klein-Gordon operator. And we would expect the functional form of the correlator to look like this. And we get something, there is some mild curvature dependence here in the distance, the Euclidean distance. But we expect something to look like, that looks more or less like an exponential. And so this is just the log of the correlator. And so so the straight line, this isn't quite an effective mass plot, but it's, you're looking for a straight line here. And if you go out too far, you start worrying about these baby universe effects. And that effect actually gets better, this sort of deviation from the straight lines from sort of early times or Euclidean times gets better as you go to finer lattices, which suggests that this sort of deviation here is coming from going to too long a distance and sort of probing this region of the lattice that suffers from these large sort of enhanced discretization effects. Or I should say the finite size effects become enhanced by discretization effects, and that gets better as you take the continuum limit. But for now, we're kind of pushing to this region. So if we do that, we can look at what the renormalized mass looks like as a function of bare mass at a number of different volumes. And so one thing you can see is that as you take the bare mass to 0, the renormalized mass is also going to 0. And this is because the lattice action has a shift symmetry as you take the mass to 0. And in fact, you can see that explicitly here in the continuum. If you get rid of this term here, this thing, it just is invariant under some shift in phi. That's also true exactly of the discretized action. And so the lattice action actually has a shift symmetry. And so, which wouldn't be true if you turned on other interactions, for example. But so things are behaving as you would expect, knowing that there's this shift symmetry. So then you might want to go on and do something else. So if you go back to, again, the 90s, there was this work of de Backer and Smit where they looked at gravitational binding on EDT near the transition, actually, at what was effectively a single coarse lattice spacing. And so we're revisiting this work with our sort of current understanding and ensembles. And so we want to calculate the binding energy. So we want to, so you can, instead of sort of going from having one scalar propagator going from its source to its sink, you could just take the product of a scalar propagator to make 2 of them, right? And so that would basically make so there's the 2 propagator correlator and the 1 propagator correlator. And the 2 propagator correlator, if they're actually, the scalars are actually bound, that should have a lower mass than twice the mass of the single particle propagator, right? So the thing that you extract from this correlation function, from the exponential behavior. And so if we just define the binding energy as 2m minus big M, where big M is the mass of the bound state, then this thing is positive in this convention. It's just to make all our binding energy plots positive. Let's assume that we want to take m, little m, small compared to the Planck scale. So we want to push sort of hierarchy of scales. So we want m to be much smaller than the Planck scale. When you do that, you would hope that you would recover the non-relativistic limit. And presumably in the non-relativistic limit, you can just plug the Newtonian potential into the Schrodinger equation in order to get the binding energy. And since this is, the solution is well known, we do it in all of our intro classes, we all do it in our intro classes. And so this is really just the binding energy of the hydrogen atom. Actually, it's more like positronium because we're assuming that the masses of the 2 things are equal. So it's just a matter of substituting alpha for alpha, gm squared, putting in the reduced mass, and this is what you get out for what you would expect the binding energy to be in the non-relativistic limit. And it's worth noting, since our lattices are effectively lower dimensional as you go, especially as you go to coarser coupling and smaller volumes, that we might be in for an extrapolation. Because in 3 dimensions, this binding energy is proportional to m squared. Okay, and in 4 dimensions, it's m to the 5th. So we're kind of, in our previous plot here, we were extrapolating, if I just go to the spectral dimension, we're kind of, numbers that kind of sit around 3 are extrapolating up to 4. Whereas for this binding energy plot, if the thing effectively lives in sort of lower dimensions, in 3 dimensions, you might expect a number around 2 for that alpha, that coefficient or that exponent. And you'd like to get a number which is around 5. So, if you really can approach the non-relativistic limit and take, the appropriate limits, infinite volume, continuum limit. Okay, so this is what the binding energy looks like. So again, this is a log plot. This is of the ratio. This is of the single scalar propagator squared in the denominator. In the numerator is the double scalar propagator. And so the ratio of these things is going to give you that difference in the exponent. And in this choice for the convention, the binding energy is positive. And in fact, you see this region, this thing is this, since we're taking the log here, you're looking for the slope of this. And if the slope of this thing is positive in the physical region, then the particles are bound. And so this is already telling us that we have a bound state. And in fact, we see this basically all of our data, that we have a bound state, with the exception of some some of the coarser ensembles. The very coarse ensemble, this thing actually, you kind of, things look a little goofy, but that's okay because you kind of expect things. It's good to actually push things to the point where they break down. And if things break down on your coarsest ensemble, then you kind of, you expect that, and that's okay. As long as things are looking better and better as you take, the continuum limit. Okay, so then you do these correlator fits, you get a binding energy, and then you plot it as a function of your normalized mass, because remember, we want to test this thing here. You can do that, and as you push down to sort of small masses, so here you get some kind of funny behavior as the mass becomes large, sort of compared to what we think is the Planck scale. But as you push things m to smaller value, to start to get a hierarchy of scales, you get something which you can fit to a power law. You get good, so all of these things, we're doing correlated fits. We get good correlated chi-squares per degree of freedom, which sort of guides our fits. And so we can get some power law for this. And this is one of our finer ensembles. And so we can extract a value for the amplitude, basically the coefficient of this power law dependence and the power law itself. And so then we can use these things and sort of plot them. So it's interesting now to take those power laws and plot them as a function of lattice spacing and volume. Okay, and so we have a bunch of points. These are all the points that I didn't show you in some of these other plots, which I took from older work. But we have a bunch of ensembles, a bunch of volumes, so many lattice spacings. And so you can see that for our very coarse lattices, especially at smaller volumes, you are in fact at 2 or below for this exponent. And that as you push to the infinite volume continuum limit, that you're starting to get up to a value which is around 5. With large errors. But I should point out that because the dependence on the dimension, you can analytically continue that Schrodinger solution, or that sort of approach to getting the binding energy as a function of m to some power to d dimensions. And what you find is that if alpha is between 4 and 6, then the dimension that implies is sort of between like 3.8 or 3.85 and like 4.1 or 4.2. So there is quite sharp dependence of this coefficient on dimension, but this is implying that we have bound states in the continuum infinite volume limit that is basically governed by the Newtonian potential in 4 dimensions. So that's kind of nice because that actually, so unlike the original, the paper from sort of 25 years ago by De Backer and Smit, we're actually seeing power law scaling, and we know how to take a continuum infinite volume limit of that. And it seems to actually agree pretty well with what you'd expect if this were really gravity. Which means that you can then take that, you can do the same thing with the coefficient, or you can extract a G Newton from that coefficient because we know what that is. And then we can extrapolate G Newton from using a similar method. And again, you get some number, which itself is not very meaningful. It's just the value of G Newton set at our, at our fiducial lattice spacing, allowing us to convert into GeV. But remember that we could do this also from de Sitter space, right? So we got G Newton by looking at basically the finite volume scaling of one of our bare parameters. And we got a G Newton, which you may not remember, but it was around 15 plus or minus 2. And so this is telling us that we can get a G Newton looking at sort of semi-classical fluctuations of the instanton, or a saddle point expansion basically of the instanton, de Sitter instanton. But we can also get a G Newton looking at the attractive interaction of scalar particles, and they seem to be consistent, and they give a lattice spacing, which is also sort of, the error is sort of order 10%, and in good agreement with each other. So that's kind of nice. So I don't know how much time do I have? Oh, I'm getting pretty close to the end. So I'm just going to conclude. So I actually just said this. So I mean, yes, the fact that we can get basically, so we get Newtonian binding, we get the right sign because it's attractive, we get the right power law because we have something which is compatible with sort of m to the fifth. You know, so suggesting the right power law for the Newtonian potential, and we get the right constant of proportionality because it agrees with something else, which is sort of this quantum cosmology thing. So that's pretty non-trivial that all of this sort of agrees. And so then you can ask, well, are you getting, is what you're simulating, like, is this really asymptotic safety? Is this a UV complete theory? Or are you just doing a really good job of reproducing the low energy effective theory? And so I would just point out that when we set the relative lattice spacing, we set it from this return probability, which gives this running spectral dimension, you know, this highly fractal thing. And so that isn't part of the effective theory. So that actually seems to capture short distance, non-perturbative physics. But since we were able to set the relative lattice spacing using that, and that's actually quite common in lattice QCD, you set the relative lattice spacing from something that's easy to measure, but isn't physical, you know, like the static quark potential or other things, you know, from gradient flow or something like that, you know, for the experts. And then you need to get a physical quantity, which is usually harder to do, to set the absolute lattice spacing. So we're just following in that tradition. But setting the relative lattice spacing, we're setting it from something which is in the non-perturbative regime. And so this suggests, the fact that this whole picture sort of hangs together suggests that that non-perturbative strongly coupled physics is actually scaling. So that suggests that whatever theory we have, you know, is not merely the low energy effective theory, but has some strong dynamics. Now, whether it's describes the real world or not, you know, I don't know, but we've already at least shown that we can get some of the things out of it that you would expect in a theory of gravity. And furthermore, the unphysical behavior of now many quantities all get smaller as you're taking the continuum limit. And so that's evidence that you actually do have a continuum limit. Otherwise, I don't know why that would actually happen. And so I would say that there's some kind of interesting support for the asymptotic safety scenario coming from lattice gravity. So I think I'm out of time, so I'll conclude there.
Thank you, Jack. That was very nice. Okay, raise your hands or you have a question. Okay, I'll start asking the question. When people do this asymptotic safety, they usually try to write some normalization group equations to get something. Do you have anything remotely similar to that?
I mean, so it's interesting to compare what people doing the renormalization group stuff get compared to what we get. Now, I haven't done any renormalization group calculations. I'm just using sort of the standard lattice methods. Excuse me. I mean, I have looked at the runnings of the bare couplings, and to sort of make sense of that, it looks like you have to do a subtraction, which is kind of analogous to what you do with Wilson fermions to get, if you want to get the logarithmic running of, you know, that you would, to reproduce what you would get in, say, dimensional regularization compared to when you have to fine tune some coupling to remove some lattice cutoff because you've broken some symmetry of the continuum theory. So you can look at running couplings, and you do get something which looks like you have a relevant parameter. It looks like in this game you only have one relevant parameter, which is the cosmological constant in Planck units. So basically G lambda runs, and that actually is, I mean, that of course would be the best case scenario, right? Because it would mean that you essentially have no adjustable parameters in your theory, and that somehow everything has to come out as a prediction. In the RG stuff, different truncations tend, it depends on how sophisticated the truncations are, but they tend to agree on there being 3 relevant parameters. Now the trouble is that they're truncating the RG equations, and so the question is, how systematic is that? Whereas once you kind of get into the scaling regime of the lattice theory, which is suggested by the good results we're seeing, that you maybe trust the lattice to have the systematics under control a little bit better, at least in terms of making qualitative statements about, and even quantitative statements, really. I mean, lattice QCD is kind of maybe not the only game in town, but for things like precision observables, for the things that Euclidean field theory does well, the lattice really is sort of the only game in town. So we are trying. So that's a case where we disagree. I can say where we do agree is that the spectral dimension should go to smaller values as you run to shorter distances.
Thank you.
And so, yeah.
June has a question, so I want to make sure that he gets it.
Okay.
Let me think a little bit, and I'll ask some other stuff later. June, go ahead.
Yeah. Okay. I would like to ask you how the phase diagram look like with respect to the Beer-Newton constant and beta, the measure term.
Yeah. Okay. So I should have shown this in the actual talk, but this is the phase diagram, and so kappa 2 is up to some proportion. It's basically inversely proportional to G Newton.
Yes.
And this is beta.
Yes.
And so this is the original sort of first order point, and then you can vary beta. And people even did this in the 90s, and they found that there was this line, and we actually sort of did a more careful job and sort of discovered that there was maybe this collapsed phase in this crinkled region, and that there was this sort of crossover, this thing that looks like a crossover between the collapsed phase and the crinkled region. And if you actually go to large enough volumes, this crinkled region starts to look collapsed. Okay, so it has this large dimensionality of the collapsed phase. But if you sit close to enough to the phase transition, then you get this 4-dimensional finite volume scaling behavior that I showed you. And so it's funny because Wilson fermions in QCD has a diagram that looks like this. And so you have this first order line, you fine tune this kappa, which is basically the bare mass of the Wilson fermion. And you have to fine tune it to this phase transition. And that's in order to take the chiral limit. But then you follow this thing to beta. Beta is the usual lattice 1 over alpha s, proportional to 1 over alpha s. And then you want to take beta to infinity. And so you want to skirt this line. I mean, if you really wanted QCD with massless quarks, you'd sit as close to this line as possible and just kind of follow it to the continuum limit. But you'd have finite size you'd have problems at finite lattice spacing with pions, for example, not being massless in the massless quark limit coming from discretization effects. So you would mess up that sort of long distance physics. And so you want to follow this thing to the continuum limit to get rid of that symmetry breaking. So I'm arguing that diffeomorphism invariance, that because these two plots are just so strikingly similar, that it's basically the same story. And so the fact that G Newton, so you might be worried that I just said I want to take kappa 2 to infinity or to very large, which is taking G to 0. And that suggests that sorry, yeah, kappa 2 to infinity, g to 0, because it's the inverse, that this is the perturbative fixed point, but it can't be the perturbative fixed point. But what happens is it looks like actually what's happening is that if you look at the dimensionless g, it's, if you sort of, scale it by the lattice spacing to construct a dimensionless g, that is going to 0, but the cosmological constant is going to infinity. And that it's actually bad, right? You don't want your couplings to diverge in the asymptotic safety scenario. All of your relevant couplings should actually go to a constant, right? That's the whole point of a fixed point. But what I'm arguing is that one of these couplings basically, or both of these couplings are multiplied by a wave, or a field strength, or wave function renormalization constant, and that it's only the constant g lambda which is the relevant one. And that there's a sort of standard argument that suggests, that shows that one of those couplings is not actually a relevant coupling, and that in terms of looking at the flow of bare couplings, it's only g lambda that goes to a fixed point, but that might be the only thing we care about. So that suggests that there actually is a fixed point, but that there is only one relevant parameter. At least that's the only way I've been able to make sense of the runnings of the bare couplings. But that's actually good news, because that would mean that there are a lot of things that one could predict, since that's sort of the maximally predictive scenario.
Yeah, actually, a related question is that I suspect that the phase diagram look quite similar in 3 dimensions as well. And so in that case, can you do the same thing, and can you take the continuum limit?
I don't know. It occurred to me to do that, but this is a pretty small effort at the moment. And I mean, we've done quite a lot. That's on my list. But I'm kind of borrowing grad students from other people and places to do this stuff. So it's
yeah. Okay. Fine. Thank you.
Yep.
Costas asked a question. Is part of the AB curve a continuous phase transition?
Yeah. So that's that's sort of the $1 million question, right? So the curve AB, there's certainly signs that it's first order. It's very strongly there's very strong evidence that it's first order, intersecting this kappa 2 line, and going above it, and even going below it. The question is, does it end at a second order critical endpoint or continuous endpoint at finite kappa 2, or do we not care if it's just sort of, in some sense, we don't care that in QCD, the way we, as lattice people, write things down, we write down beta. It's okay. In fact, it's desirable that this thing, is at beta, the endpoint is at beta goes to infinity. And so it may well be that you have to take kappa 2 to infinity. And I've argued that that isn't actually g going to 0. It's just g lambda going to a fixed constant. And so the question is that endpoint a continuous phase transition? And so to study that is, it's really a question of calculate everything you know how to calculate, and see if your lattices are scaling, and you can measure physical quantities, and discretization errors are going away as you take that limit. So really you need to do this sort of whole body of work to see if that's true or not. Because it's not possible to simulate at kappa 2 equals infinity. I mean, you just can't do that in your computer, but you can study scaling as you follow this curve out to that. And of course, the difference between what we're doing and in QCD is in QCD, you at some point make contact with perturbation theory, whereas we're not making contact with perturbation. Perturbation theory works for gravity in the IR. So there's a nice low energy effective theory, but that's not going to tell us how the UV behaves.
Are there any other questions? I have one more. At some point you mentioned that there might be some diff invariance that is broken. Is there some word identity that you can test that on?
That's a good question. Yeah, I thought about that a little bit. a few years ago, and I haven't thought about it since, but it's actually a very good question.
Okay, anyone else? Okay, let's thank Jack. Great job, thanks. I presume that now we continue in a discussion. More generic. Okay, so anyone else? Maybe people are tired and they want to go home to sleep.
Okay, then can I ask a general question? So
Go ahead.
what would be possible, I mean, beyond just showing that this is asymptotic safe theory? Can you get some physical predictions for quantum gravity that is measurable, or?
Yeah, we're working on that.
Yeah.
Maybe at the next one of these things.
Okay.
No, actually, I mean, yeah, I mean that's really the $1 million question. So we're working on that.
Mm.
I'm going to be a little coy.
Okay, then can I ask another question about this? Well, exact renormalization group studies. People introduce higher derivative operators, and
Yes.
that of course make this unitarity problematic. But do you have such a concern in your approach?
I mean, okay, so there's sort of, two issues here. One is this thing unitary? And so, and it's not so easy to see in the sort of Euclidean path integral formulation. Now, one of the things that you can do, or that we can do, is we can compare to this causal dynamical triangulations, where this is this other lattice method. So they get very similar results for sort of de Sitter space, semi-classical fluctuations about de Sitter space. They haven't looked at binding of scalars, but they, for example, the spectral dimension, my study of that was sort of motivated by them. In fact, my study of all of this is in some sense motivated by them. So, there are things that look sort of like universality, but the nice thing about their calculation is because they have an explicit time slicing, which maybe you think you shouldn't have to put in by hand, but maybe if you do, it's okay. But with that explicit time slicing, they can show that this, they have a positive definite transfer matrix. So they have sort of, the equivalent of unitarity in Euclidean space for their model. So they can show that, whereas I don't. And in fact, I have these sort of branching baby universes, which are worse and worse as we go to coarser couplings. And so it looks like that sort of effect is going away as you take the continuum limit. So, there's some hint that maybe you're recovering unitarity, but you're breaking it at finite lattice spacing, whereas they kind of bake that in from the outset. But if we're in the same universality class, then it doesn't matter. And so you want to test all the things that are actually continuum predictions in our theory and their theory, sort of see whether whether you're actually reproducing a result which is gotten from an explicitly unitary theory. And then your other question, or the other part as I interpreted it, I'm trying to think. So is it, let's see, sorry, can you repeat your question?
Well, I think you answered my question already, but
I was going to make another point, but I forgot what it was.
Yeah, I was asking about the introducing higher derivative operators.
Oh, higher derivative operator. Yeah. So it looks like we don't need to introduce the higher derivative operators in order to take the continuum limit.
Yeah.
Which suggests that they're irrelevant. And so, so if they're interesting, sort of F of R gravity, if that, which is interesting phenomenologically. And so if that's real, if they actually play some effect, when the curvature is large, then that would, in principle, be a prediction of our theory. or of this theory, rather than just another input. So that's something one can look at.
I see. And talking about the universality to the causal dynamical triangulation, in their approach, they don't introduce the measure term, but what do you think about it? What do you think about it?
Well, they're also having issues trying to find a continuum limit.
Yeah.
And it's possible that they need the measure term. I mean, they may have, by having the thing be explicitly unitary, they may have cleaned up some of the stuff that sort of has to happen as you take the continuum limit. And maybe they have to do a different fine tuning, right? Because now they have anisotropy. And so maybe they have to, again, fine tune to recover the isotropic model and the continuum limit, which is different from my fine tuning. But it's possible that they still need that measure term. So, that might actually help them, but I don't know. I mean, I thought about doing it myself at some point, but, again, human power issues.
Yeah, okay, thank you very much.
Yep.
So maybe I can ask one question, Jack.
Yes.
So, Jack, do we have any analytical input? Like, has somebody done any analytical calculations on this?
Well, so the renormalization group stuff is sort of semi-analytical. I mean, you write down these operators. You often, in the end up solving them numerically, but that tends to be a sort of, throw it into Mathematica rather than, run on a cluster for months.
Right.
Sort of thing. So it's sort of semi-analytical. Yeah, but it's difficult to get at. I mean, you can do other things, right? You can do an epsilon expansion in the number of dimensions, right? Expanded about 2, which is something that Weinberg did, back in the 70s in his sort of groundbreaking or sort of, seminal work on this. But then, of course, you have to analytically continue epsilon, a 2 plus epsilon expansion. You have to, set epsilon equal to 2, which, is a bit cheeky if you actually want to, say something about 4 dimensions. So yeah, if it were more analytically tractable, I think, this problem would have, there would have been more progress on this problem years ago.
Right.
Jack, can I ask another question related to higher derivative operators? I think it's nice to see that the continuum limit is possible in your approach, but you have to make sure that this is not just R-squared gravity, right? And do you have evidence for that?
Evidence that it's not R-squared gravity.
Yeah.
I mean, the evidence is, I mean, we're just putting in the Einstein-Hilbert term and a CC term, plus I argued the reason for this measure term. And I mean, the evidence is, if you look at sort of what is the physics that's coming out. And so, I mean, that the Sitter Instanton thing suggests that whatever is coming out of, whatever emergent, is emerging from the sum over triangulations actually looks like, semi-classical gravity with a CC term and the Einstein-Hilbert term. And then again, you're getting, you reproduce Newtonian binding, which also is sort of coming from the Einstein-Hilbert, I think is coming from the Einstein-Hilbert term.
Okay, let me put my question in another way. Okay, R-squared gravity is a perfectly renormalizable theory, although it has the problem of ghost. So I think you should be able to reproduce R-squared gravity in some way using dynamical triangulation approach. But I've never seen such things. So it would be possible, well, if it would be possible to reproduce R-squared gravity by dynamical triangulation, that would be a kind of indirect evidence that you're seeing something different.
Yeah, I mean, the thing about R squared gravity, I mean, you can show, you know, that if you add the two R squared terms in 4 dimensions, that those are asymptotically free.
Yeah.
Now, the thing is, or one of the issues, and I would say is a little bit, is you're sort of assuming that you can do perturbation theory there. And one of the things that we find is that once you get, and you know, if you look at the running of G lambda, what you find is, oh, and that perturbation theory is about flat space, right? And so if you look at our running couplings, this G lambda at the fixed point becomes of order 1. And so what that's telling me is that in the regime, the non-perturbative regime that we care about, where the, you know, the issue of renormalizability and what's really a relevant coupling and all of that needs to be addressed, the cosmological constant is becoming of order 1. And so, you know, I don't think it's necessarily valid if some of your couplings are becoming non-perturbative, even if, you know, you can sort of treat some of them in a perturbative expansion. It seems like the set of assumptions that's going into R squared gravity it runs into issue, you know, it could run into inconsistencies if G and lambda, I mean, you sort of posit that lambda is going to 0 or is 0 just sort of from the beginning. But if it has some non-trivial running, then I don't know that you can, you know, make that perturbativity or whatever assumption. And so that suggests to me that what we're seeing is different, and that it accounts for non-perturbative physics that isn't sort of built into the perturbative R squared calculations.
So do you think that it is not just a technical problem that you cannot see R squared gravity from dynamical triangulation? Or you think that, well, this is rather a conceptual problem?
Well, I guess what I'm saying is that R squared gravity, I mean, we could just throw in an R squared term, but if my picture is correct, then that's just going to be one more, you know, irrelevant coupling. So that's going to be like a Clover improvement term, or, you know, whatever in the, you know, some rectangle in the gauge field, and it's not going to change the universality class. What I'm arguing is that it's hard for me to see how R squared gravity is going to give you the non-perturbative running of the cosmological constant in the UV, and you know, I don't know how you would account for that. So as soon as some of your lower dimensional couplings in the R squared theory, you know, if in our theory those, you know, that thing becomes non-perturbative. So I just don't see how you'd make contact with perturbation theory in the sort of marginal operators if the relevant operators are, you know, becoming strongly coupled.
Yeah, there is a question from Costa.
Yeah, why beta has a negative value. So yeah, I don't know why beta, it looks like, and you can kind of extrapolate beta to the continuum, and it looks like it's sort of ballpark -1. I'm not sure why that is the value that it is. I mean, you can do this, this Fujikawa, as I said, that, you know, you can fix beta in the continuum, and that sort of depends on how you treat, you know, the ghosts, and, you know, you do a sort of gauge fixed BRST formulation and get and extract what beta is, and that also ends up being a negative number. The thing is, I don't know how much of our root G to the beta you have to put in by hand, and how much is basically given implicitly by the sum over triangulations. But I can say that the beta value that Fujikawa comes up with is, I forget what it is. I think it's like -3/2 or something. So it's, I mean, some of that, you know, the fact that they don't agree perfectly suggests that there's some amount of this root G to the beta that's sort of baked into the sum over triangulations, and then the rest has to be put in by hand. But a negative value doesn't seem preposterous based on the Fujikawa argument.
Any more discussion? Okay, I think we're done. Thank you, Jack. Thank you, everyone. I guess we'll see you all tomorrow. Okay. Take care.